Are you coming to us from Minnesota, Cal?
Sorry, what's that?
Are you coming to us from Minnesota?
Not quite. I'm from San Diego.
Oh, jeez. Well, good for you.
He lives next to Chad, almost neighbors.
Okay. Well, this is February 2nd, 2026, and this is the 7 a.m. Western Automation Technical Class weekly event. And this week, we have the honor of Cal Coker from Turk, who apparently lives in San Diego and not in Minnesota, much to his credit. And Cal has a discussion today for us on networking IO, which is a big deal. More and more of an important topic as the years go by. Um, I'm of the opinion that it's a great way to get involved in a system such that we can then fan out and address a lot of the other components attached to the network. If you rule the network, you have an ability to touch all the pieces of the puzzle, and that means the controllers, the servo amplifiers, the servo motors, the other sorts of drives, all the sensors, et cetera, et cetera. So I think this is a piece of knowledge for people in our profession that's key. You got to be knowledgeable about this if you want to have another entry point into the design discussion at the customer level so that you can affect other components. With that said, Cal Coker from Turk, thanks for coming, Cal, and it's all yours.
Welcome. So I'm going to go ahead and share my screen. You guys got me?
Yes, I can see your screen. It says Intro
Yes.
to IO Link.
Yes. So a minor deviation, we'll be talking about networks, but this is more of a introduction to IO-Link and then a overview of something I build up to travel around with. So welcome all. My name is Cal Coker. I am the Western Region Field Bus or just generic application engineer. Started with Turk in June. And I've been a controls engineer for more than 30 years. Prior to Turk, I was with Omron as a field engineer for 16 years, and then Delta Tau before that, and Precision Microcontrol as a motion control application engineer back in the 90s and early 2000s. Anybody who's looking, here's my contact info. Please don't hesitate to reach out at any time. And my general policy is if you've got a question, you need a quick answer. I know it's old school, but pick up a phone and call me. If you have something you want to document, throw it in an email, I'll get back around to it. But to me, the cell phone is now like my bat phone. Just give me a call and I'll be there. So, yes, as the new guy at Turk, I was focusing on different technologies that either line up with what I've done before or that looked really interesting, and IO-Link was a little bit of both. So we'll kind of do an introduction to it and then go over a little bit of hardware that I've got available to travel around with. IO-Link was released in 2009 as the first global standard for smart sensors and actuators. IO-Link's wiring is based on the industry standard 3-wire sensor actuator connection. So just a little bit of a clarification. IO-Link is a point-to-point connection system. One sensor goes to one cable, and get this thing out of the way here. There we go. A 3-wire cable. It is not a field bus. In fact, IO-Link is not even a network. So here's a traditional, overly simplified diagram of a sensor connecting to a PLC, usually via 3 discrete wires. So now we're going to show you what you'd be looking at doing it differently with IO-Link. So we've still got the same sensor, still got the same PLC, but now we are inserting an IO-Link master that is stationed between the sensor and the PLC. And this will concentrate the data from all of the IO-Link devices, pack it into a Ethernet-based message going to the PLC to update the PLC with status. So it's about as simple as it gets. You add a newer version of a sensor with a communication built into it. You add a little interface device called an IO-Link master, and now you can take old machines and get more data off them, or this can be your architecture for a new machine. So IO-Link is a new type of sensor, a smart sensor, if you will. We can ask the question, why just do on or off when we can now do so much more with IO-Link? Yes, for the first few years, IO-Link was expensive, but not anymore. In most cases, you can get an IO-Link sensor that still has both on and off if you want it, and they cost about the same as they used to. So there's no cost adder for this additional information you're getting. It includes sensors that are generally now offering analog output for things like measuring distance, pressure, and temperature. The sensors are programmable with multiple set points on trigger points. It is specifically designed to support Industries 4.0 with built-in device diagnostics. And IO-Link is Turck technology that you should be selling every day. Hooray. Okay. Global market for 2025 was estimated at $15 billion. By 2023, it's expected to grow up to $48 billion. There are over 500 IO-Link vendors, and they're producing more than 20,000 IO-Link compatible products. So let's go over some of the basics. So IO-Link is a 3-wire traditional sensor connection between 2 devices. And the first device, it all starts in IO-Link with that sensor we were looking at. It can also be an actuator, but generically, when we talk about IO-Link, we usually use the term sensor just to simplify things. And then as we showed in that animated diagram earlier, the added component of the solution is an IO-Link master. And basically, the master just sits between the sensor and the PLC and formats the data. One of the things to keep in mind, because it's not a network per se, is if you add another sensor, you are then going to be adding another cable. So here we have a traditional IO-Link system with sensor, cable, and IO-Link master. And then we can just add that connection between the IO-Link master to the PLC, and we are good to go, and we're now back up and running. The physical connection is between the sensor and the master. It can either be an M12 cable pre-connected like shown here, or we can just go old school with 3 simple discrete wires, power, ground, and signal, going between the sensor and the master. And then here we're just demonstrating that, again, this is not a network system. You've got your master, and then for each new sensor that you add, you're going to be adding in another cable, and there would need to be an available port. In this case, this Turck Ethernet or IO-Link master has 8 ports on it. So now we've got 2 of them utilized, and we would still have 6 more ports available. The standard IO-Link M12 connector pinout. This one is from an inductive sensor that is on a demo that I will be showing off a little bit later. You've got your We use the term 3-wire cable, but in some cases that may be more or less depending on the sensor. But basically, you've got pin 1 is 24-volt power, pin 3 is ground. Pin 2 is typically not used for IO link, but the standard does make a facility for that signal. And then pin 4 is where our IO link data is coming in. So the signals labeled out 1 and out 2 would generally only be used if your user either chooses to use an IO-Link sensor but not enable IO-Link, or maybe they have some sort of a special purpose sensor that doesn't support IO-Link. So one of the important things to walk away with here is, yes, we're trying to tout the powers of these new smarter sensors, but the IO-Link environment does still support the old school Boolean on-off sensors.
Cal, I've got a question.
Yes,
A
sir.
couple of questions, actually. In general, you said that this is a Turk developed technology, and yet it seems to have been generally accepted by the industry. So
I must have misstated that. No, I'm not in any way, shape, or form trying to say nothing we're talking about right here is Turk specific. The only thing is at the top of this page where I'm showing this wiring diagram, that is the diagram from a Turk IO-Link analog sensor that I will be addressing later. But no, this is so far this is all global and IO-Link and everybody's kumbaya and having fun together.
developed it originally.
Gotcha. Anything else?
Yeah, who developed it originally?
It was originally, well, the overriding company was Profibus Profinet. So,
So Siemens?
honestly, my research did not specifically say Siemens. Profibus Profinet, my understanding is that is an independent organization that defines and manages the spec. But thank you.
And then one last question. You say this is not a network, yet there's digital data going out on line 4, I guess, right? Or coming in on line 4?
In general, the idea would be a network is something that can be expanded upon with the existing backbone. So if you've got an Ethernet network, you've got a computer or PLC with the RJ45 Ethernet port, but we've got a network out there that I can drop multiple devices onto. It's all using the same cable. With IO-Link, that's why I use that diagram that showed for an additional sensor, you need an additional cable. So the topology of the signaling and the wires, you expand it with each new device. So
and that leads up to my last question.
Yeah.
IO-Link, you're forecasting a pretty significant growth for it. And why versus networking the sensors? Why is this better?
Well, the networking of sensor is more of an overriding high-level architecture type of thing. Let's say Ethernet IP or EtherCAT. Whereas a lot of the things that you can do with IO-Link that you can't do with the other, let's say, more industrial networks is that with IO-Link, we can take an existing sensor with existing connections. Sensor could be 30, 40 years old, and they can go get a new sensor. So there's a lot more MRO type of opportunities to do machine improvement. Whereas on a more traditional network, you're going to have to redesign the backbone. All the part numbers are going to change. It's a much smaller incremental jump and a smaller cost to going into IO-Link than it would be with any of the other networks.
Thank you.
Let me
Yes, sir.
interject quick one statement too, which is it's probably going to be a long time or never that your actual bottom line end of the line sensors are going to be Ethernet natively. That's a lot of infrastructure stuff that goes on. That's a lot more expense. Like Cal said, now you're starting burning up IP addresses and things like that. So that's why this kind of subnet exists to handle all the base data layer.
Thanks, Chad. All right. How about we move on now? So real quick, like a little bit of under the hood, what's going on in IO-Link is there are actually 4 different types of data transmitted over IO-Link. We have our process data. This is the good stuff that we're really trying to get. This is what is the sensor doing and seeing. This is updated on a cyclic basis at a maximum time frame or minimum time between updates is 2.3 milliseconds, but it's also outputting um, values or status, so we can get things like a checksum to confirm internally that the data we're getting is good. There is a built-in mechanism that the device will be broadcasting its part number, serial number, version number. This is not intruding on the cyclic operation. This is upon a request from the PLC. And then the last thing, we also have a facility for intermittently transmitting warnings and errors. And again, this would be triggered by a flag from the PLC. The process data is actually what we're really interested in. And in order to maximize network speed, IO-Link has been specifically designed to keep the messages updated cyclically, or you could call it every scan, as small as possible to keep the throughput and the bandwidth as high as possible. So for example, on that same inductive sensor we were looking at before, it's generally going to be transmitting 16 bits from the sensor to the IO-Link master. Bit 0 is going to be reporting one of the user-defined set point statuses in there. Bit 1 will also be transmitting the status of a single sensor set point. And then the last 14 bits of that 16-bit message, this is the actual data being sent over IO-Link. It's essentially your analog signal. So a few summaries items. It's IO-Link is a point-to-point communication, 24-volt logic, standardized on 3-conductor unshielded M12 cables. Maximum length from device to device is 20 meters. But with each new device that you add in there, you're extending the total cable run from a sensor back to the PLC. Minimum cycle time or scan rate is 2.3 milliseconds. And IO-Link does support both the old school 3-wire sensors that could be 30, 40 years on a machine, as well as the new smart IO-Link devices. Let's talk about some of the advantages of IO-Link. First and foremost is the ability to upgrade machine performance by replacing old school on-off, or what we could call Boolean sensors, into an IO-Link sensor with analog. That means we're getting more data, and that more data makes our machine smarter and more valuable. It's using standardized pre-built point-to-point unshielded cables, which reduces wiring time and wiring errors, which will then result in a faster machine startup. And the startup time will be significantly reduced. IO-Link is a platform and operating system independent. We don't care if you're running an Allen Bradley PLC or an industrial PC, with code assist on it. And we don't care if you're using Windows or Linux. IO-Link is independent of all of that. You get more data at no extra cost. You get more robust connections, so we have reduced maintenance over a long period of time. IO-Link includes a really cool plug-and-play device replacement facility that if it sees that a sensor has died and been replaced, it will automatically download the original parameter configuration of the old sensor and upload it into the new sensor. So there's essentially no No effort required out of maintenance to replace a sensor. It will be retaught by the IO-Link master. And you do have the option on machines to mix and match the smarter, more intelligent IO-Link with discrete wired devices. They can actually be put together on one machine with the same IO-Link master. So you're not going to IO-Link doesn't lock you out of special purposes you might have done in the past. And it has built-in diagnostics to help with predictive and preventative maintenance and to reduce downtime. And you can also access IO-Link device parameters remotely. So it facilitates machine upgrades and repair.
So Cal,
Yes, sir.
quick question, just for clarification. What you're saying is that when you have an IO-Link master, you don't only necessarily have IO-Link devices hooked up to that. You can also have standard discrete or analog devices hooked up to the same master and have a combination of devices hooked onto the same master device.
Absolutely correct. Yes.
Yeah. Thank you.
And it keeps the customer from being forced to make an all or nothing decision one way or the other. This allows them to have more flexibility in the architecture and the bill of materials and the functionality of their machine.
And what you're getting from the devices that are hooked onto that master that are actually IO-Link, you get a lot more data from them, a lot more information from that sensor than you would from if it would just be a standard analog or discrete output sensor.
Absolutely, Chris. Thank you.
Mm-hmm.
So we'll take a little bit of a turn right here, and now we're going to talk about something that's a little more Turck specific. So we now understand that if you're going to put IO-Link onto a machine, you're going to be adding a device called an IO-Link master. In the Turck world, our IO-Link masters support multiple protocols, which in this case would be, I'm going to use the network name Ethernet IP, but it's usually associated with Rockwell. We support Profinet, which is usually supported by Siemens, and then we've got Modbus that is a more open standard and not talked anything. The really cool thing that we're getting out of this with Turck's multi-protocol is that all of our sensor and IO-Link master part numbers change regardless of what Ethernet communication protocol you're using to talk to the PLC. So we'll start off with one example. We've got our sensor, we've got our cable. These two part numbers are going to be the same no matter what the host PLC is. We've got an Ethernet, or an IO-Link master, and in this case, we can connect up a Siemens PLC talking Profinet to this block, and this IO-Link master has the multi-protocol built into it. It auto-recognizes the incoming message format is Profinet, and it accommodates it internally, locally, and automatically. But let's say tomorrow we want to build a different machine and we're going to use Allen Bradley. We can use the same sensor, same cable, same IO-Link master, and now we just connect it up to an Ethernet IP device. We're going to have to obviously pre-configure the Allen Bradley PLC to communicate to tell it this device is out there, but the IO-Link master itself auto recognizes and changes its protocol on the fly to match the PLC. Next day, we can go in and switch it, and we can say we want to talk Modbus. We could even go to something like a Turck CodeAssist PLC HMI that has the capability of speaking any of those three protocols. So this is really where we're talking about the power and flexibility of Turck's multi-protocol capabilities. And now we'll go over a couple of Turck specific IO-Link masters, and that really all does come from that multi-protocol capability. So with the same sensor, the same IO-Link master, we can talk to Allen Bradley, Siemens, Codesys, Beckhoff, Omron, ABB, pretty much any PLC PC that supports industrial Ethernet is already built into the Turck IO-Link masters. Again, we also have independence from the protocol itself, Ethernet IP, Profinet, or Modbus TCP. With Turck, the IO-Link master has a free built-in web server for easy sensor connection, configuration, and testing. No need to go out and buy extra software to monitor or configure your IO-Link system with Turck. And then when using Profinet specifically, because Profinet is kind of the guiding body, or if you will, of IO-Link. IO-Link and Profinet have some additional built-in features where things like your IO mapping is already pre-built in. So here we'll just give you a quick overview. I usually don't like to inundate people with a whole bunch of part numbers, but over here right now on the left-hand side, you're getting an overview of the different footprints and styles of IO-Link masters available from Turck. You've got your more traditional rack systems, both in cabinet and out on the machine. We've got the Turck IO blocks and the IP67 footprint format, and then also the FIN 20, which is a cabinet-based discrete wiring solution. And then we can jump over and just try and overwhelm people with the fact that, as you can see on this list, we pretty much have every type of sensor that you'd be looking for. A lot of these I've already connected and tried setting up on IO-Link, and we have a very complete and system available for whatever your applications might be. And that is it for the first presentation. Any questions while I open up our next short video here? All right, well, let's move on. And in this presentation, I'm focusing on a demo/test unit that I built. This is kind of the way I tend to learn. I need to get my hands on it. So the idea was to buy a demo that would specifically accomplish two goals. One would be suitable for training and demonstration for reps, distributors, and customers about IO-Link, and the other was just to be able to give me a real world like hands-on experience. So I built this demo, first came out late October, and this is the demo board size itself is 24 by 17. The headpiece HMI PLC is removable. And so we'll just kind of go over what's on this demo and hopefully impart some ideas as to why and how I did it. So we start off over here, up here in the left-hand upper corner, we have a small IO-Link master that is interfacing. Here we've got an inductive IO-Link sensor connecting to the IO-Link master with a M12 cable and then just a pigtail on the other side. We have a Turck IO-Link capacitive liquid level sensor, also with analog output, and we'll be using that in a later demonstration to measure the depth of a jar of liquid representing like a vat on a machine. We have a temperature sensor with a remote temperature probe on it. And then we have our Turck TX207 Codesys PLC HMI. Some of the other devices on here, I do have a number of different lamps. And so I've got two digital output modules that are just driving indicator lamps on the panel. Turck 24-volt power supply, another digital output module. In this case, this one is controlling 2 solid-state relays for a temperature control system. And there are the solid-state relays right there, and a remote temperature probe. This is reading temperature created in this little black plastic box that we'll get a look at inside here in a few minutes.
So,
So here-
Cal,
Yes, sir.
your IO link masters in this, when you go back one slide, would be those FEN20s up top, not our block style TBENs, correct? So these are your
Correct.
IO link.
Yes,
And then,
thank you for pointing that out. My original concept, we'll see if it goes forward, but was actually to build 2 of these. One was kind of built on a panel-based concept, so using more discrete wiring. The second panel was going to be using or emulating the on-machine distributed remote I/O with the IP67 blocks.
yeah, so for everybody, the difference is these are the in-panel IP20 DIN rail mount. They're just here mounted to the board, but they can be DIN rail mounted. And then there's, of course, the field style that is IP68 or 9 that you can put anywhere outside or on a conveyor. Or so we have different form factors of these IO Link masters. This is just one of them that you see here on the board. Cal, this one that we see on the board, does it have the web server as well, or does only the block style have the web configuration server?
They all have the web server all built in and ready to go.
Okay. Thank you.
Yep. So here's our diagram. I drew this up for me to build it up, but if anybody out there is looking for some ideas, I'm more than happy to provide all the materials. I've got the bill of material is actually on the board. So if anybody wants to go out and build up something similar, more than happy to help you get it done. So now we'll take a little more in-depth look at the 3 different IO-Link circuits on the demo. The first one is an inductive sensor, and it has a range of 30 millimeters. Here's the sensor right here, and then this is a plate, 1/4 inch by 3 inch by 3 inch metal. And this system can measure from 0 to 15 millimeters. On the HMI, you'll see that right here, I've got the raw data that we're reading from the sensor. That is a 12-bit value. And then I've also in the PLC scaled that to report the distance in millimeters. And then we've got matching LEDs on the HMI as are available on the demo here. And when we get to the video section, I'll give you a little bit of a demonstration of what I call the dirty sensor test. The videos will be after we go through the quick overview of each different circuit on the board. The second IO-Link sensor is a liquid level sensor. Sensor is right here. Its tip would be submerged into this brown liquid, which is actually Coca-Cola because it gives me a higher density measurement. And the value the sensor can report is from submission level of 0 up to 100%. On the HMI, again, we've got matching lamps on the HMI as we do here on the demo board. And then I just used a bar graph to translate the physical level of submersion of the tip into the liquid. And when we get to the video for this, we'll take a couple of minutes and show you how to utilize that web server to make parameter changes. And then the third circuit on the demo is a true heat and cold temp control zone. So with the IO-Link sensor, temperature sensor right here, and then a remote probe that goes into this black box, this will allow the PLC to then take the value written over by the temperature sensor, which right here you can see is 120 degrees. And then we'll be able to use the PLC and some of the other circuitry here to both heat and cool this environment. So here's a picture inside the demo. And basically you can see that I've got some old school C9 Christmas tree lamp sockets with 28 watt, 120 volt bulbs. These bulbs are typically used as the light bulbs in a microwave. And then over here on the side, I have two 24-volt fans, so I can alternately heat this temperature box and cool it down. On the HMI, again, we're providing the user with feedback as to translated temperature into both Celsius and Fahrenheit. I've got some manual controls, and then over here on the right-hand side, that's where we'll be able to activate the circuit and demonstrate true temperature control. And then for coming attractions, before we get to the videos, I just started working on a really cool new safety block that Turck has coming out. It's a TBN module with SafeLink, and it includes each of these blocks has its own CPU, safety PLC inside of it, and it's programmed with Turck Safety Configurator software. Has 4 built-in ports here. Each port can support 2 safety inputs. And then we have 4 output ports that can either be safety or non-safe. And then the really cool thing is we can distribute up to 31 other blocks daisy chained together to get a large distributed safety system. And it does also support the multi-protocol of Ethernet IP, Profinet, and Modbus. So that'll be my next topic when we once again meet. So this gives you a quick photo of what the typical safety code would be. And this is actually the phase 1 of the demo that I'm building. So these 3 ladders of code right here fully implement the e-stop. We've got a non-safe digital restart button for your safety. And then over here, we have a force-guided relay with a lamp on the outside. And this is emulating and representing the ability to control machine power with a safety control system. So I look forward to introducing you guys to that in the future. So let's now go and take a look at a couple of videos. So the first video we're going to look at here is just going to give us some operation. And here we go.
Cal,
Yes, sir.
we cannot hear or see, or at least I cannot hear or see a video right now.
Yeah, I can't either. When you shared your screen, you probably there's a little button up top that says include audio. You may want to reshare.
Yeah, if you stop sharing your screen and then when you click reshare, it'll give you a little checkbox where you can say include audio.
Sound? Okay. See if we got it. Can you guys hear me now?
Physical movement of
Yes.
the
Yes.
target.
Yes.
Perfect.
Object,
Thank you, guys.
Which is a
We didn't miss
1/4
much.
inch thick steel plate that's approximately 3 inches by 2 inches. You can see that it is riding on a 2-inch plastic standoff that allows me to slide it back and forth. And then we also have our lamps here. And in this case, the red LED, the red lamp tells us that we're either too far out of range or too close. When the green lamp is on, that is telling us that we are within the valid range of the sensor, which with the current settings, the maximum read distance is 15 millimeters. When you get to within 2 millimeters, there's a bit that is configured in the sensor to say that the object is too close. Now, in the upper right here, this is a VNC viewer. This allows me to connect my laptop directly to the HMI screen on my PLC. So we're seeing exactly the same thing that we are seeing when you look at the physical demo. You may notice there is some tape on the standoff. And also up here in the VNC screen, I created a little animation so that as I move the sensor, or sorry, the target object, you will see the distance of this leading edge surface to the sensor. And then you'll also be able to see the raw data from the sensor as well as the scale data. So I'm taking this value and scaling it into millimeter units. So for example, if I just slide this over until we get the green light, and we look up on the VNC viewer, and you can see that the raw reading is a count of 36, 15 to 20, somewhere in there. And the green lamp is on, telling us that the object is detected. And down here, you can see that it's converting this value of 3612, which is a 12-bit value, into millimeter units. So as I move this down a little bit, and we'll get down around, so right now we're at 5.5 millimeters. You can see the scaling is fairly close to accurate on here. And down here you can see, I know the green lamp isn't quite as high intensity as the red, which is as blinding as the sun. But you can see the distance of the target object to the sensor head. If I move it all the way in, you'll notice that both the green lamp and the red lamp are on. That is because one, the target is still detected, but the minimum distance setting in the intelligent IO-Link inductive sensor, I believe it's set to 2 millimeters. And so we're also getting an object out of range because it is too close. So we'll back off a little bit. And that gives you an idea of basically everything that we can do with this inductive sensor, except for one really cool little trick that I will show you in the next fairly short video. So one other thing I wanted to show you about the inductive sensor demo that I've got here is what I call the dirty sensor test. So years ago, when I first heard about IO-Link, one of the things I was told is its benefits in regards to proactive preventative maintenance on machines to maximize uptime. And it seemed like a great idea, but I never really seen it before, didn't know how it worked. So I just kind of went along with it because, to be honest with you, I hadn't used IO-Link before I got the Turck. So when I started building this thing up, I wanted to prove to myself that it actually made sense. So I've got something pre-configured here. If we look down here at the actual demo itself, you'll see right now that we got the red light on. So we know the target object is out of range. If we look up here on the VNC screen of the HMI, you can see that it's currently reporting a raw value of 4095, which is the maximum value that it can read, which means it's out of range. And it's also in scaled units reporting 15 millimeters. Now, the practical reality is it really means 15 millimeters or more. So I wanted to come up with something to prove to myself, and if it worked, then kind of make for a cool demonstration of something. So I created what I call a dirty sensor. This is basically 2 or 3 inch square plexiglass, nothing fancy about it. In the middle of it, I've got a mixture of garage metal shavings and oil and dirt and a little bit of Vaseline just to kind of keep everything contained. But I also knew that I had never tried something like this, so I also built up my control for the experiment. This is the same plexiglass material, just nothing in between it. So what we're going to do first is confirm that when I insert the plexiglass up against the sensor head, that you can see up in the VNC screen that there is no change in the reported value being returned by the sensor, which is what I would have expected, since the sensor is supposed to be detecting metal and it's supposed to have the capability of reading through other objects. So now I'm going to take the sensor with the gunk on it, and I'm going to put it in here. And all of a sudden, if you look up in the VNC viewer, you will see that it is actually changing the reading, and it's actually indicating that the object is closer than it really is. Take it away, we go back to full signal strength and no object detected, but I put this in here and all of a sudden the value drops down to, what are we looking at, around 3,900 or 14.4 millimeters. Take it back away and we see that the value drops back. So to me, this confirms that you can indicate if the sensor is getting invalid readings. And you could also, as a part of your machine maintenance, either just proactively regularly clean the sensor off, or in your PLC code, you could have like a calibration procedure where you put the target object in a specific location, and then you could measure the reading. And in this case, we know right now that it should be reading 4095 or 15 millimeters. And in this case, if I just wiggle it forward just the littlest bit, we've also confirmed that when you move the target closer, it is working correctly. You only have a problem when I put this gunk in front of it. The other question you may ask is, well, why does the red lamp turn off if the VNC is showing me that I now have a reading of the device, but I don't have either the green or the red LED on? The reason for that is there is a set point, initial set point programmed into the sensor that is set to 3,800. So putting this object in front is moving the measurement range between what it should be, which is 15 millimeters or more, and now it is in between the sensor detecting that something is present, but not within the threshold that is programmed into the device. Thank you.
Okay, so now we'll take a quick look at the liquid level sensor.
Now let's take a look at the capacitive liquid level sensor demo assembly shown in this photo right here. On the demo, we have the sensor itself connected via M12 cable over to the IO-Link master. We have a small jar filled with water. I usually use Coca-Cola because it's a little denser. I get a stronger signal. But in this case, I figured water would make it easier to see the submersion occur. The switch over here toggles the actuator to extend or retract. I've got lamps over here. The yellow lamp is associated with a parameter setting for liquid detected. It turns on right now at 30%. In the next video, I'll show you how to change that with the Turck web server. And here I've got the green sensor, which is associated with what we would consider for the application full immersion, which right now is set to 75%. So let's go ahead and utilize our VNC to activate the HMI buttons. I'm going to click on the home button and switch from the inductive to the liquid level sensor. So here we have our screen. Up here we have a value that we are reading directly from the sensor, which reports a value of 0 to 100%. It's currently reading 7, but that's basically just noise. There's nothing there. We have a bar graph that will give us a graphical display of the values here. And these two lamps are directly tied to these two lamps. And these are bits coming directly out of the sensor itself. So first thing we're going to do is just go ahead and move the actuator down and submerge the sensor tip. We now have our yellow lamp on, which tells us we've reached the minimum immersion for what we would consider liquid detected. The green lamp is also on, meaning that we've exceeded 75% immersion. And there is also a companion LED built into the base of the sensor as well. These two are tied together. So now I'm just going to fully retract the sensor, and then we'll just run this down a little bit until we just trip the liquid detected. And you can see this time I caught it, it's at 48%. Unfortunately, because this is a simple on-off or extend retract actuator and a physical switch, it's not that easy for me to try and place it at an exact location. But that's the capacitive liquid level sensor, and thank you.
So I have one more short video, and this one we're going to reopen that discussion of using the web server to change parameters and settings within the sensor.
So let me show you how to change parameters inside the IO-Link sensor using the built-in Turck web browser. So I have a new Chrome browser window open, and I am going to type in the IP address of the FIN20 IO-Link master. So we can see right here, there's our address, 192.168.1.50. Obvious in the real world, this can be set to any number of different Ethernet IP address ranges, but this is what my FIN20 is set to, and this is the browser. So first thing I'm going to do is log in, and it is password, all lowercase. Hit enter. Yeah, because it's a dumb password, they're going to chatted to you about changing it. And now I go over here to what's called the IODD configurator. And the first thing we'll see up here is over here on the left-hand side, it shows us, remember the FIN20 has 4 IO-Link ports. So it shows me I have my inductive sensor connected to port 1, nothing on port 2. And the NCLS, that is my capacitive liquid level sensor. So I'm going to select that one. And you can see it gives me the vendor and device number, some basic information about it. In this case, we're going to go down and select parameter. And what we're going to be looking at and what we're going to be toggling and changing is what's called output number 2. And this is mapped to the yellow lamp on both the HMI and on the demo itself. And output 2 is what is used for the liquid detected, and output 1 is what is used to determine when we have reached maximum desired immersion. Now, what you would do in that with your PLC is completely up to them. But what I want to do here is to show you, we're going to minimize this for a minute. Again, we're looking at the liquid capacitive sensor right here, and this little pop-up says we're going to show you how to save a parameter via the web browser. We've got everything set up, and right now we're at 32% immersion, and both of those LEDs are on. So I'm going to go back and reset this, and I am going to set, we've got the switch on threshold. I'm going to set that to 45%. You'll notice when I enter a value, it gives me a little pencil here. It tells me it's been changed, but it hasn't been written to the sensor. And here I'm going to go and set this to 40. So now I set what I want the parameters to be in the sensor, and I am going to write that data over. What I want to do is to point out what's going to happen is we have now raised the minimum threshold above what it was, and specifically above what the current level is, which is currently set at 30% to turn on the yellow LED. So I'm going to refocus on here. Don't need to change anything else, but because the current reading is 32 and the minimum reading for turning on is 45%, I'm going to go over here and click on write. And that data is now saved and configured. And now you can see the LEDs have turned off. And now in order to get to that minimum level, now I'm at 57%. The yellow LED is now on, but the green is not because I haven't reached that minimum threshold for full immersion, which is set at 70%. So I'm just going to move this down a little bit. There you go. We're reading at 90. All is good. Now you understand, you use your built-in, your whatever browser you want to use. You open it up. You're going to set your IP address. So I am directly connecting my laptop's Ethernet port to the Ethernet port on my FIN20 IO-Link master. And that's all there is to it. Thank you.
All right. Well, thank you folks for listening in. Anyone have any questions?
So Cal, this is a transportable demo. I assume fits in the back seat of your car or something?
Yes, yes, I've actually kind of standardized on a size. I've got a large hard shell suitcase, and this fits into one side of it, and that safety demo that I'm building fits into the other. So I've kind of standardized on a size. I learned years ago that when you're a roving, traveling field engineer, you got to have the ability to bring lots of hardware with you. So, so that's the plan.
Well, that looks very well executed. You mentioned a couple of future classes. The one that perked my interest was the Turk capability and safety controllers. Um, do you mind just dropping me an email and listing the class subjects, and I'll put you into the schedule?
We'll, we'll do that. I'm gonna actually I'm working with Chad on that, so we'll be coordinating the components and the upgrade from phase 1 to phase 2. So I will definitely let you know.
Got a few slots available in about 6 or 8 weeks, so let me know.
Will do.
We'll, at Western Automation, we'll be at the WAI Tech show this week in Anaheim. I'll be there Wednesday, and I'll be up in Vegas at the HVAC show on Tuesday. So anybody wants to connect at the show, just drop one of us a text on our cell phones. And with that, Cal, thank you very much. I look forward to your next class. It's 8:04, time to go to work, and we'll see you guys next week. Look at the schedule that I put on the email on Sunday for the upcoming classes. Thanks, and have a great week.
Thank you.
Thank you, Kyle.
Thank you, guys.
Thank you, Cal. Thank you, guys.
Thanks, Cal.